Okay. Convergence for Cauchy integrable functions. This is theorem 2.5.1. So if you have a sequence of functions, and they're continuous and they converge uniformly to the function f on AB, and f is Cauchy integrable, and the Cauchy integral is equal to the limit of the Cauchy integrals of the individual functions. So what we're doing is commuting or reversing the order of taking the limit and doing the integral. So you want to have a function like this available. If you're going to integrate a series term by term, you need to have this in order to justify, right? This theorem is a justification of integration of a series term by term. Okay. So what's this business about uniform continuity? Can somebody please define that? Given a sequence of functions, f, n, they're all defined on some set E, which could be a bigger space. It could be a metric space or something like that. Let's just, for the moment, consider E to be a subset of real numbers. So we have all these functions f n defined here. We say that fn converges uniformly. This is the notation, the pointwise limit. So for a particular x, you evaluate fn of x for a particular x, and you run the ends out, and then you get some limit, right? So it converges uniformly, pointwise. There are other forms of convergence, but pointwise. Huh?
Uniformly to pointwise?
Well, yeah, it converges uniformly to the pointwise limit f. F is the pointwise limit, i.e., the limit as n goes to infinity of fn of x is f of x. Okay? Okay. So this means that this convergence is uniform. And what exactly does that entail? Maybe we should take a moment to look at something that isn't uniform. Closed at 0, open at 1. f1 of x is equal to x to the 1. f2 of x is equal to x squared. f3, f4, blah, blah, blah. Okay? I claim the pointwise limit of fn of x is 0. And I also claim that that convergence is not uniform. Okay. We believe this. Well, do we believe that the limit, pointwise limit is good? Can we show that? We have to. Well, let's see. Yeah, we have what we have to do. What we have to do is pick. Must show for some. Let's call it y in 0, 1. The limit as n goes to infinity of y to the n equals 0. Okay. Right. To do that, for all epsilon greater than 0, must find an n of epsilon such that little n greater than n of epsilon implies y to the n less than epsilon. Okay, we always do that. And we take the natural log of both sides. We have n ln y less than ln e epsilon, ln epsilon. So if, let's see. Right. I would like to divide by ln y. Now, if ln y is going to be less than 1, or y is less than 1, so this is negative, so n has to be greater than ln epsilon over ln y. Okay, so it suffices to pick n of epsilon equal to ln epsilon, ln y. So I have gone out and found my bogey there. As long as I'm bigger than that, y to the n should be less than any preassigned epsilon. And I claim that y is totally general. It's between 0 and 1, not 1. Okay. So this ought to work. This one?
Yeah.
Well, actually, you have to say, I think it's the first integer large.
No, didn't I say? But I'm just assuming n is greater than that. N is greater than that. Okay. Yeah, it not being 1 saves me, because if y were 1, the ln would be 0, and then I'd be out of luck when I try to. I could do this, right? Obviously, as I get closer and closer to 1, this becomes closer and closer to 0, and amps this thing up. So it requires a huge n to push this thing down.
Right.
Out here, right? Okay. Now, I don't think this is uniformly
Very close
convergent.
to 1. Delta 1 on the negative side.
You haven't calculated? Do a numerical example if you want to show you just how this is. Suppose I pick 0.9 as y. And suppose I want to be within 0.001 of 0. Then what would my bogey n of epsilon be? It would be the natural log of 0.001 divided by the natural log of 0.9.
Okay.
65.5?
It would be the next one up. It would be the 66.
Yeah.
So I would need y to the 66 to push it down there, right? Y to the 66 or any higher power would be below 1/1000th at 0.9. Just a numerical feel of what's going on there, right?
Understand?
Okay.